We are now live. Okay, you guys are not particularly exciting about that. I think I'll request a sign, on the door, like a little red light, on air, when we're actually on air. Well, I hope you guys have a chance or had the chance to review the material before the class, because so far we have made the connections from physical quantities and physical devices like electrical charges, relays, and transistors. Okay, so we made that connection from physical stuff to logical stuff because we just made a NAND gate in the previous class using two N transistors and two P transistors. So are we okay with that concept? Okay. And then in the previous class, I mentioned that you can use NAND gates to make all of the other gates or all of the other operators that we are used to in cisp360. So that's what we'll be doing today first, and also your lab is to take a look at the NAND gate and find out, okay, so given these NAND gates, what good is it going to do us? Okay, because we don't use NAND in C and C++ programming. So that's the first thing we'll do. And then the second thing we're going to do is to move on and talk about base conversion. In other words, after today, we will be on values, numbers, and bases. So as far as your reading assignment is concerned, you probably want to get that done, before next Monday, okay? Because this is what we'll be on today. All right. Are there any questions? No questions. Okay. If there are no questions, I'm gonna get started here. And if anyone has problem, accessing the material from the website, let me know, because somebody not from this class just told me that he was not able to access the class material. I gave it a try in Firefox and also in Chrome, and there was no problem. But if you encounter problems, just let me know, because I know Chrome and Edge now wants everything to be done by HTTPS. So if a page is connected by HTTP, it will mark it as insecure, but it should still display the content nonetheless. But if you have a problem with your browser and it refuses to display the content because it's going through HTTP but not HTTPS, let me know and I will try to figure out how to reconfigure your browser, or I can just add HTTP links. Is that okay? So in this case, you can tell that the browser has a little bit of an issue. It has a little exclamation point, in a circle, to complain that basically this is not an HTTPS connection, which also means all the routers and everybody who can eavesdrop in my connection would know that my laptop computer is looking at this content. I don't have a problem with that. Okay. After all, this entire lecture is streamed to YouTube in public. So it's not an issue. But in some other situations, it might be an issue that you may not want other people to know what you're viewing. It doesn't have to be something inappropriate. It just has to be something that you do not want other people to know. Like login credentials, but that's not the only thing. That's kind of a security issue, and definitely, it can be something as simple as I'm checking out vitamin supplements. Okay, it is nobody else's business. As long as you think it is nobody else's business, it should be a privacy issue. Okay. Okay, so enough about that. We're moving on, and so we talked about what a transistor is. There are two kinds. There's the N-type transistor, and then there's the P-type transistors. And we built the circuit in the previous class and also in the lab. We analyzed what the circuit is going to do depending on the inputs. If both inputs are zeros, the output is going to be a 1, and so on and so forth. And then we constructed a truth table of the 4 possible combinations of input and the corresponding output to those input scenarios. And then we concluded that this looks kind of like a conjunction or and, but it's not because it's the exact opposite of and. 0 and 0, or false and false, is false. But it's a 1 over here. 1 and 1 of true and true is true, but it's false here. True and false is supposed to be false, but it's a true here, and so on. So everything is negated. So that's why it is. So what the gate is doing, by making the gate out of two p transistors and two n transistors, is it is doing the negation of a conjunction. Okay, so to express that using C syntax, well, we call the output W. So W is basically, it's basically the same thing as the logical negation of the conjunction between X and Y, and XY being the inputs into the circuit. So are we good so far? This is a quick recap of what we talked about on last Wednesday. Are there any questions? No questions? Okay. So now we move on, and yes, absolutely.
So drain would be like the ground?
So, okay, so the naming convention of drain versus source, right?
Yeah.
Okay. Okay, let me see if I still have Zerno in here. Yep, I do. All right, so we'll make a new page. There we go. Okay, so as far as the terminology of a transistor or field effect transistor is concerned, a transistor looks like this. Okay, now this is an N-type, but the P-type, just has a bubble right at the gate, and there's an arrow. The arrow is the significant part because the arrow always points from source to drain. Is that okay? So it depending on whether this is an N-type transistor or P-type transistor. What you see right now is an N-type transistor. With an N-type transistor, the flow that we are measuring from source to drain is negative charge. So when you're dealing with an N transistor, the source is the part that is experiencing a lower voltage. But when it is a P-type transistor, which means there's a bubble here, then the source is positive charge. And the source has to connect to a higher voltage source compared to the drain. Is that okay? Does that kind of answer your question? Okay. Go ahead.
So that means like, I'm just used to working with like an Arduino. So
Okay.
negative voltage, you can just call that ground.
Yes.
And you can call the positive voltage like the 5 volt.
The supply. Yep, VCC or it usually is called VCC or VDD in a circuit diagram.
Okay.
Yep, go ahead.
Should we always assume that the source is going to be on the top of the gate and then the drain is on
No, because when we used the N-type, the P-type transistor, the source is on the top. But when we use the N-type transistor, the source is at the bottom because the convention is ground is usually at a lower position. So in the circuit diagram, we also kind of follow the convention. You can draw a picture any way you want because a schematic is nothing but a logical diagram of how things should connect. Because we naturally think of a lower voltage at a lower place visually and a higher voltage at a higher place. So in most circuit diagrams, VCC or the positive voltage is displayed on the top and then ground is displayed at the bottom.
So is negative voltage no voltage or just a lower voltage and you're positive?
Well, everything is relative. So in the case of ground, it is considered the 0 point of the entire thing. But relative to power, relative to VCC, it is the lower voltage. It is at the lower voltage. So as far as the transistors are concerned, it really is the question of is electrons flowing in this direction? In the case of an N transistor, and in the case of a P transistor, it is a positive charge flowing. Yep. Yeah, it's very confusing because in electricity, the flow of electricity is opposite to the flow of transistors. It's exactly the opposite. It's just a naming convention issue.
Gotcha.
Yep. All right. So, any other questions? Yeah, this is way beyond what we actually need to know because we are software people and these are pretty hardware stuff. But I do want to kind of start the class with something that is completely grounded, as in physical devices and physical quantities, so that we can kind of feel that connection to the low level stuff. Okay, so section 3.4 is saying that, well, you actually do not need negation, conjunction, or disjunction if you have NAND. Okay, the same can be said about NOR, but we'll start with NAND. Okay, so now the question is, well, if you are only given with a NAND operator, how do you implement the other operators in C and C++ that you are already familiar with? Okay, so what we'll do is we are going to, okay, I'm just erasing everything from here. So what we'll do is we'll define something first, okay? So by definition, I'm going to do this. X and Y is defined to be the negation of X and Y. Is that okay? I'm simply defining a new operator NAND using existing operators that you know from CISP 360. So, so far? Okay. So this is just a definition. There's no reasoning behind a definition. So now I want to ask, if I want to implement negation on its own using NAND, how do I do that?
Could you for and could you do not x and y? The not.
But not itself is not one of the things that we are supposed to use. So we are supposed to find out how to use NAND to implement not. Yes?
Like x and x.
X NAND X. There was another hand. Same thing, okay?
Negation of x and x.
But excuse me, we're not supposed to use negation. We can only use NAND. Yep. So you guys are correct. Okay, X NAND X is the answer. Okay, so I claim that this would do the trick. But let's find out whether it does the trick or not. Okay, there are two ways to answer the question. One is to do it by Boolean algebra, and the second one is to do it by a truth table. Okay, so we'll do it in both ways, and you guys can decide which way is more convincing to you because different people prefer a different method. So I would do it using algebra first, or Boolean algebra. So by definition, this expands now to the negation of X and X, right? And then I utilize a theorem that says X and X is X. So now we get that, okay? So we'll say because X and X is just X. I'm sure there's a particular name for this particular axiom in Boolean algebra. I just do not know the name of that axiom. So that's one way to do the proof. But some people may say, but I want the other proof. I want to prove this by a truth table. So when you prove something by a truth table, the first thing you need to do is to identify what your independent variables are. Independent variables, as the name implies, are variables that are independent to each other. When one particular variable has a particular value, the other variables can have whatever value they want as long as it meets the type requirement. Okay, that's what I meant when I said independent variables. So in this case, it's pretty clear that we only have one variable. It has to be the independent variable x. And then on the other side, we say, okay, if I know what x is, do I know what is the negation of x, which is what we want to achieve. And we also want to know what is x NAND x. Now, x NAND x is by definition the negation of x and x. So we want to work out these columns. There are basically three columns. The first column is x. The second column is the negation of x. And then the last column is what we think implements the negation of x, but only using NAND. Okay, x can either be false or true because it is Boolean. The type of x limits us to only two possible values. When x is false, not x is true. When x is true, not x is false. The second column is pretty easy to work out. The last column, okay, I'm just going to move it over here, is we first have to evaluate x and x. When x is false, x and x is also false. But we also have to apply the negation after that. So not false is true. Okay, we'll put it through here. And when x is true, x and x becomes true and true, which is true. But we have to put the negation on the result of the conjunction. So not true is false. So do we now understand how we come up with a truth table? Okay, and the meaning of the different columns of the truth table. Are we good so far? Are we convinced that the second column and the third column have exactly the same value for each row of the truth table? We are. Okay. So that in Boolean algebra, this is all you need to prove that two expressions are equivalent. You just have to show for every possible case of the independent variables, the two expressions come up with exactly the same value. Then they are equivalent. They are the same. Is that okay? All right. So with this in mind, our next task is to say, well, let's try something harder. What about x and y? Okay, how do we express x and y using just NAND? Yep.
Since we've built the negation, we let negate the
Exactly. So we are going to use something that we have already done. So I'll put this into a two-step process. Okay. There are several ways to look at this. Okay. So I'll do it step by step and see if you guys would agree. I'm going to do something that's kind of dumb and seems to be useless. Would anyone argue about this equivalency? Remember, exclamation point is negation. The negation of negation, well, it cancels out, right? They don't do a single thing together. Are we convinced? Okay. So then on the next line, I'm going to do just adding a little bit of parentheses. Would that be okay? I'm simply indicating the order of applying the negations. Okay, which was applied earlier, on the first line, but now I'm making it more explicit. Are we good? Do you see a NAND, at least one NAND on line 13? Look at the definition of NAND and look at the pattern, the expression we see on line 13. Do you see any resemblance? Yeah, because,
but it's not
but exactly, we would have the negation left out, right? Because if you look at just this part here without the outermost negation, that by definition is x NAND y, isn't it? Look at line 1. All right, so, okay, so looks like we can do some work here. Can we agree that this is the conclusion? Line 13 leads to line 14. Can we, just because of the definition of NAND? Okay, all right. So now we have to deal with the negation. We have one single negation operator on the outside that we want to get rid of, right? But because we just said, hey, the negation of x, and x doesn't have to be a single variable. It can be a huge, big, long expression. The negation of something is that NAND itself. Yes? Exactly. So we apply that trick to what we know about the negation. Then we just say, oh, it is blah, blah, NAND itself. What blah, blah are we talking about? X NAND Y. So we take this, and we put it on both sides of the outer NAND, and we're done. So this would be hard to say because if I just say it out loud, in a linear fashion, it is x NAND y NAND x NAND y. It doesn't really quite tell you what the order is because the parentheses can be done in different ways if it just said that. So it is much better to, refer to the expression using parentheses. And this is personally why I do not like infix notation, because it relies on parentheses to indicate the ordering of operation. Much prefer postfix notation where there's no ambiguation whatsoever. Yep.
So the line from number 14
Uh huh.
is equivalent to the line from 7, just on
The line from 14 to 15, I am using the result on line 3.
oh, okay.
Yeah, line 3 is how we do it. Line 4 and 5 is the proof of why it works. Yep.
So we built the NAND 2 circuit. How would the X NAND X circuit work? Would you have to build something in parallel with our NAND circuit?
Okay, so let's take a look in Logisim. Okay, and I'm gonna get rid of what is already here, because whatever is already here I can easily reproduce. Okay, so we do have a NAND gate. In other words, when you do this type of experiment, well, your homework does involve the use of your own NAND gate, but for illustration in class, I'm just gonna pull a not NAND gate like this. We want to change the. Okay, click one.
So that's the one we built.
That's pre-built. Yes.
Okay.
So we want to limit the input to only 2 pins and change the gate size, which is really just for display purposes, to a narrow like that. So if you want the same result as negation, you give it one single input because there's only one independent variable. You give it one output, which is the result of the expression. And I would even use labels to remind us what it is. This is just variable x, and this is supposed to be the negation of x. Okay. So this is the circuit, and I'm going to talk about the connections later. We switch back to the expression, which is this one here. The gate is NAND, and we want the 2 inputs into the NAND gate both to be x, right? So when we switch back to the circuit, we just go like, oh, okay. So this goes to both inputs of the NAND gate. This one, and here's the other one. Is that okay? So now the NAND gate is taking x, which is the input, as both of its inputs, which is the equivalent of using x on both sides of the NAND operator in an expression. Okay? So now we connect the output to the output pin, and then we ask, well, is it working? Well, fortunately, in this case, there are only 2 test cases. When x is false, not x is true. Okay, that works. Excuse me. And then when x is true, not x is false. It works. Yeah, yeah. This is why I like Logisim, because it can take whatever we are talking about, in the lecture, in the notes, as an expression. It would turn it into a circuit. Then you can play with it and actually watch it, see how it works. Yep.
So in a computer,
Yep.
I understand it's made up of a bunch of transistors. Would it have like sections for different gates, or would it make its own gate? How does that?
That is a good question. Okay, so there are different types of chips or different types of chips to implement a processor. With your Intel processor inside a computer or the ARM processor in your cell phone, they are customized. In other words, they optimize the use of transistors to implement gates. So they're not going to use NAND 2 gates to make everything. They would actually use, whatever is the least amount of transistor to implement whatever logic needs to be implemented. Is that okay?
Oh, okay. So do they know, like on average, they need this amount of AND gates and this amount of OR gates?
Um, so the translation from gates like and, or, not, nor, NAND, and so on, to actual transistors, that's done by what we call a silicon compiler.
Oh, okay.
Yeah, so it's not even done by hand, it is done by a quote unquote compiler. So the compiler would look at the description of the circuit, like how the AND, OR, and NOT, and NAND, and NOR gates are connected, and it will figure out the optimal way to implement the whole thing in transistors.
Oh, okay. That's cool.
Yeah, there's no way a human can actually, or a team of humans can design a modern processor by hand, transitioning from gates to transistors. And the reason is quite simple. Let me show you a Google search. Okay, I haven't done it, so this is the first time I'm doing this. So we'll look at the Gen 8 i7 transistor count. Okay, so there we go. Uh, just under 3 billion transistors. This is a ninth gen. Okay, it's not eighth, but it's the latest generation of um, processors. It's an i7 with eight cores. The die size is just 174 millimeters squared, which is not a whole lot. Okay, because 13 times 13 is 168. Okay, and 13 millimeters is about just a little bit, a hair more than half an inch. So that means if you look at your thumbnail, okay, I think my thumbnail is about average size, and that's about half inch by half inch. That is the area that we are talking about. That is going to have just under 3 billion transistors. So if every two people in the world is making one transistor, then the entire population on Earth is just enough to make up the transistors inside an i7 processor. Yep.
So this question. So when people won the silicon lottery when overclocking like CPUs,
Uh
how does
huh.
that play into how many transistors? Like, do some just not work, or like how does that work out?
How does you mean? So you're asking how does overclocking work?
No, I know how overclocking works. I just wonder how, because I know that you can have two of the same CPUs,
Mm-hmm.
and when you overclock them both, most likely you're gonna have different results. Is that due to like what is that? What does that do to?
It's due to manufacturing variations. So if you look at how processors are made, they are photo etch. There's a whole big process to make it on what we call a die. Um, uh, Actually, on a wafer. So a wafer is a circular type of silicon material. Um, it's usually 300 millimeters or 30 centimeters in diameter. So just kind of imagine a disk about this big, okay? And they will try to make as many devices on the wafer as possible, okay? Because they want to optimize manufacturing cost, right? So on that disk, they will try to fit as many processors as possible. So after the manufacturing, they will break out these chips, and each one will be tested individually. Now, because of manufacturing variables, okay, some of these chips, even though it is from the same wafer and manufactured exactly the same way, they still have minor differences. So some transistors are slightly bigger, some are slightly smaller, and so on and so forth. And as a result, when they test these chips, some can be clocked to a certain level, and some can only be clocked up to a certain level, a lower level, reliably. And this is how they throw these chips into different bins. Okay, this one can be clocked all the way to the highest possible clock rate. They throw it into the most expensive bin. Look at the second tier and go, okay, these are in the second bin, these are in the third bin, fourth bin, and so on. So the lowest performance, but still performing and still not entirely faulty ones, would go to the least expensive bin. Is that answering your question? Yeah, so it really has to, it's not about the chip design itself so much as how they test each one after manufacturing to find how much they can clock it. It's kind of like when you go to a supermarket and you buy, say, peaches, right? So you can have, let's say, 200 fruits from the very same peach tree, okay? But the farmer, may decide and go like, well, these look really, really good. We'll put it into the $2 per pound bin. And then these look kind of not so good, but they don't have any actual blemish. They just don't look as good as the other ones. We'll put it into the $1.50 per pound bin, right? So it's the same thing with processors, except they don't evaluate by the looks of the chip. They look at how fast they can clock it reliably, and to throw them into different bins. Is that
Yeah, no, that
good?
answered it.
Okay, cool.
I'm gonna ask you a little bit more.
Okay, if the class does not mind kind of diverging from the main
Yes.
topic, that's okay. Go ahead.
So, as my understanding of this question was like what physically, because like the peach tree, sunlight causes the difference between peaches.
The other.
The source of the difference. That is a clarification of the question, I believe, if I'm correct. What's the physical cause?
There are many. There are many reasons why it can be different. Like the etching process is chemical. Is chemical based. So depending on how the solution gets circulated, and also the temperature distribution during that process, different parts of the same wafer can experience a different rate of getting etched. And the concentration of the can also be different, depending on how it's agitated, how it's circulated, and so on. So the manufacturing process itself has a lot of variables involved that can affect different parts of the wafer differently. And I think that really contributes to why chips behave differently, even on the same. Now we have more variables, right? Because between wafers, the base material or the substrate material can come from a different batch. So this batch of silicon may have more or less impurity than the next batch of silicon substrate. So there you have even more variables between wafers. But even on the same wafer, you can still have a lot of variables. Is that good? Okay. All right. So yes. So to quote Forrest Gump, okay, chips, getting chips out of a wafer is like a box of chocolate. If you don't know what I'm referring to, watch that movie. Watch Forrest Gump. All right. So we got and implemented now. So getting back to our notepad. Okay. So we got and. So now it's time to move on to or. Or is a little bit more involved because we need to talk about De Morgan's law first, because that is one of the things that we need in order to derive the equation. So it's called De Morgan's law, okay, plural, because there are technically two laws involved here. So I'll give you the two laws. So law number one, okay, states the following: if you look at the negation of x and y, okay, this really is the same, or so it claims, the same as not x or not y. That is the first law of De Morgan's law. Now, which one is the first one? Which one is second? I have no idea which one is supposed to be first. But there are two. So in English, it says not x and y is really the same thing as not x and not y. Not x or not y, excuse me. Yes, correct. Thank you. And if somebody tells me that verbally, I cannot process it. Okay, I don't process spoken words very well, so that would not have convinced me that they are truly equivalent. To some people it does. Okay, to some people it is intuitively the same. Okay, but to me, that does not work. So I would need a different proof. Okay, it is already stated that this is true, but how do I prove it? What do you think? Boolean algebra would be a little bit harder in this case because you're trying to prove one of the axioms in Boolean algebra. Truth table, very good. So we can actually prove this using a truth table. I'm going to do it one more time, just so that we get another exposure of how a truth table works. So when you look at this particular equation, how many variables are involved? There are two variables. X is one and y is the other one. They are independent. Okay, there's no interdependency between the variables. X does not depend on y does not depend on x. So when we construct a truth table out of this, okay, we have two independent variables. How many possible combinations of values can we get out of this? 4, exactly. Because when x is true, y can be true or false. When x is false, y can also be true or false. So we end up with 4 possible combinations. So, I usually just do it like this, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, you can do it in a different way, but this is just the usual way that I do things. So these are the 2 columns of quote-unquote inputs into the equation. They are basically the 2 independent variables, and each row is saying, what if x has this value and y has that value? What happens to the expressions that I'm interested in? And just like in the previous case, the 3rd column is one of the expressions that I'm interested in. And then the last one is the other expression that I'm interested in. Okay, so now we have 4 columns. And then right now, it's just chore that we have to evaluate each expression for each row. When x is false, y is false. False and false is false. Not false is true. Okay. Not false is true. Not false is true. True or true is also true. Okay, moving on to the next one. False and true is false. Not false is true. Not false is true. Not true is false. True or false is true. This one, the next one is just a mirror image, so it's going to end up with exactly the same result. And the last one, let's work it out. X is true, y is also true. True and true is true, not true is false. X is true, y is true as well. Not true is false. Not true is false. False or false is false. Are we convinced that the 2 expressions that are of interest to us turn exactly the same for all possible inputs to the expressions? Well, as weird as they may seem, they are actually equivalent. One is exactly the same as the other. Are we good so far? So this is one particular law of De Morgan, and then the other one, excuse me, the other one looks almost exactly the same, except we flip the and the or. So these are the 2 components to De Morgan's law. So some people count these 2 as one single law, and some people count them separately and say it's De Morgan's laws. Okay, so as far as I'm concerned, as long as you understand the equivalency of the expressions, that's all we need. Are we good so far? Yes? Okay. So once we understand De Morgan's law, then we can start to work on what is x or y and how to express it using only NAND. Okay? So the first thing I do is, once again, kind of like a dumb thing to do, because I'm just applying double negation, which doesn't really do anything. But that's also why I can introduce it even though it was not there originally, because it doesn't do a single thing. It's just like in arithmetic, or not arithmetic, but in normal algebra, you can say something and then you can say, oh, but it's the same thing as something times 1. It's kind of like that. So then the next thing we do, just like last time, is to put in extra parentheses. So we are now explicitly stating which negation occurs first and which one is the second. And now we recognize one of the equations of De Morgan's law can be applied? Is it 1 or 2? What do you think? The second one, 2, right? Because the second one here on line 27, it says if you see a negation applied to a disjunction, you can now transform that into a conjunction of some kind, and then you negate whatever was inside the parentheses. Is that okay? So this part is more, once you are convinced of De Morgan's law, this part is just recognizing that a portion of the expression on line 30 can apply, we can apply De Morgan's law to that expression. Okay, so let's go ahead and apply that. So we can't do a single thing about the outermost negation yet, but we can apply De Morgan's law and say, oh, the inside is now that. Oops. Is that okay? Are we convinced that we have just applied line 27, which is a part of De Morgan's law, to the expression on line 30? We good? All right. Well, I see at least one thing that's familiar to me. I see how we can also apply line 1, which is the definition of NAND, because I see this negation applied to the result of this AND.